Greetings! Today we're going to explore where the number e comes from. Now the number e is a very important number in mathematics, and it has a numerical value of approximately 2.718281828, and then so forth. Now it looks a little bit, if you just judge it based on its first few decimals, as though there is a pattern. However, the number e is irrational. So an irrational number is a number whose decimal never repeats. There's never any pattern. So another example of an irrational number would be pi. So pi has a decimal expansion that goes on forever without any pattern or without repeating. Another example of an irrational number is the square root of 2. So although it looks like there's a little bit of a pattern in the beginning, that pattern diminishes and it just becomes a random, not random, but an apparently random string of numbers without any discernible pattern. So we have this long infinite expansion, and it's a very important number, as we shall see, in exponential growth. So where does it come from? To answer that, let's go back and think about compounded interest. Compounded interest. So suppose we have an initial investment, so we'll call this the initial value, and we'll use the symbol A to represent the initial value. And then we have let's say, an annual interest rate of R. So this would be in percent per year. So for example, if you have 4% interest, so 4% per year would yield a value of R as 0.04 for 4%. And then further, suppose that we compound interest n times per year. So we have an initial value or an initial investment of $8 in a savings account with an annual interest rate of R% per year that is compounded n times per year. So if it's compounded quarterly, n would equal 4, and every quarter 1% interest would be applied, right? Because it's 4% per year, so we divide that by 4 times per year and we would get 1%. In general, so every time interest is compounded, we have to multiply the previous balance by a factor of 1 plus, let's see, it's going to be R over n, right? So a factor of 1 plus R over n. So again, if R was equal to 0.04 and n is equal to 4, so that's 4 times per year, we would be multiplying by 1.01, because 0.04 divided by 4 is 0.01. So that's 1/4 of the total interest every time the interest is compounded. So that formula was 1 plus R over n. And the first time it's compounded, you just multiply it by a. So this would be, for example, p of 1 over n, right? So if n is equal to 4, p of 1/4 would be a fourth of a year. So it's after the first time interest is added, we have this amount in the bank. So p of 0 is just equal to a, that's the initial amount. P of 2 over n would equal a. So we take this amount here, and when we multiply it by 1 plus R over n again, so we get 1 plus R over n squared, and so forth. P 3 over n, we get a 1 plus R over n cubed. Because every time we add interest, we simply multiply by 1 plus R over n. So in general, if we have P of t, so we have to think about this a little bit. So what it should be is n times t. right? Because if t, the way to think about this is if t is equal to 1, we have exactly compounded interest n times. So whatever this exponent is, it should equal n when t is equal to 1. Similarly, if t is equal to 1/2, we should have compounded interest n over 2 times, so the exponent would be n over 2 and so forth. So this is the formula for compounded interest n times per year. So this is interest compounded n times per year. Now, the next question is, what about something called continuously compounded interest? So what happens if we take this interest rate of r percent per year, and apply it continuously? So instead of applying r at discrete moments in time, we apply interest continuously. So instead of waiting until the end of the month, applying interest at the end of the month, we would be applying interest every single millisecond. So what happens there? Would you end up with an unlimited amount of cash in your savings account, or is there some upper limit as to how much you can actually get in terms of interest with a fixed interest rate if you apply or compound the interest on a continual basis? So what we want to do is look at the behavior as n goes to infinity. So the idea is we want to think of a, r, and t as fixed. So for a fixed initial balance, for a fixed interest rate, and for a fixed final period of time, what would happen if we compound the interest more and more often? So instead of compounding it 10 times per year, maybe 20 times per year, or maybe 100 times per year, maybe 365 times per year, that's once per day. Maybe 1,000 times per year, maybe 100,000 times per year. What's going to happen as we compound it more and more often in the limit? So we'll see what that term means later on in the chapter, but in the limit as n goes to infinity. In other words, as n keeps getting larger and larger and larger, what is happening? Will it grow without bound, or will it level off at some amount of capital at the end of the period? So we'll think of a, r, and n as fixed, or a, r, and t as fixed, and then we'll let n just get larger and larger and larger. So the trick here in our, let me rewrite the formula. So we have a 1 plus r over n to the nt. And the whole trick here is to multiply that by r and divide it by r, just like that. And then we'll introduce a new variable. So introduce a variable, we'll let x, and we'll let x be n over r. So this is kind of like a scaled version of n. So remember, r is still a fixed constant, but now x is equal to n over r. So if we want to understand the behavior as n goes to infinity, it's the same as letting x go to infinity, right? If n is getting larger and larger, then x is getting larger and larger, right? 100,000 over 0.04, 1 million over 0.04, a billion over 0.04, still getting larger and larger and larger. And so let's rewrite this where we see the x. So the amount of money at time t would equal a 1 plus 1 over x to the x r t, right? So here, so what are we? So here we have r over n. So r over n would equal 1 over x. And then in the exponent, we have n over r. So we take these two, and those two become, that's just equal to x. So we have x times t times r, and then we have a 1 over x right here. So this one becomes the 1 over x. And we notice that we have a quantity that no longer depends on any of the other parameters. So we have something that only depends on x, and then whatever this is, it's to the power of RT. Right? So the idea is what happens as this, so what happens as x goes to infinity of that quantity. And using the notation of limits, what we're really asking is what is the limit as x goes to infinity of 1 plus 1 over x to the power x? Again, we haven't introduced limits yet, but essentially it just means what's happening to this function. So here we have a function of x. Function of x. What's happening to that function of x as x gets larger and larger and larger? So to answer that, I'm going to use an Excel sheet to just get an idea of the answer. So I started off with 1, and I'm going to say equals b2 times 10. So 1 times 10 is 10, and I'm going to pull this formula down so we get larger and larger values. So this column would be the x values. And then my next column is going to be values for 1 plus 1 over x to the power x. So we're going to evaluate, for these values of x we see on the left, we're going to evaluate this function 1 plus 1 over x to the power x. So for here I want to say equals, start a parenthesis, 1 plus 1 over b2 to the power of b2, and we get the number 2. So with this function, the function 1 plus 1 over x to the power x, if I evaluate it at x is equal to 1, I get 2. If I evaluate it at x is equal to 10, I get 2.59 something. In other words, if I compound interest 10 times per year, this would be that number. It would be this to the power RT. Well, let's keep going down. 100, 2.7, it's getting larger. 1,000, 2.72 approximately. 10,000 times per year, 100,000 times per year, 1 million times per year, 10 million times per year, 100 million times per year, 1 billion times per year, 10 billion times per year. So we see that this number, this 1 plus 1 over x to the power x, is not becoming arbitrarily large. It's not getting larger and larger and larger. It's leveling it off, 2.71828. And it's getting closer and closer to this number that we call e. So we can literally say that this is the definition of e. So this limit is literally the definition of the number e. And then when we replace this with e, our formula, let me just write it in red over here. So we get p of t is equal to a e to the rt, just like that. So the number e replaces this stuff right in here. So basically the number e is used whenever interest is being applied continuously. And it's not just interest. We use that because it's a simple example to understand. But anytime you have something that's interest-like, so it's growing at a rate of r, but it's growing at a continuous rate. For example, when you have carbon decay, or you have decay of radioactive isotope, it's decaying on a continuous basis. Right? A radioactive isotope isn't going to wait and only decay once every quarter, like you might get interest dividend in your bank account once every quarter or once every month. No, a radioactive isotope is going to always be decaying. At every moment in time, it's decaying a little bit at a time at a given annual rate. So we would use exponential, this number e, to describe that. And this is exactly where the number e comes from.